Hello, everyone, and welcome to your channel of Math Made Easy. Today, we are going to learn another method of solving a system of linear equations. Remember, we did the Gauss-Jordan elimination method before. Today, we are going to learn a new method, and this method involves finding the inverse of a matrix. So, what is the inverse of a matrix, and why do we need it? The problem is that in matrices, which we will cover later, you can apply addition, subtraction, multiplication, but never division. So when I write three equations, say, of equilibrium, usually, I mean, two is trivial. So let's say 3 by 3. So you have three equations and three unknowns, and you want to solve and find the values of your uh, variables, x, y, z, for example. If that was algebra, so if I tell you, for example, 6x equals 18, you say divide both sides by 8 and x is 3. Yeah, you would be right. But the problem is we don't have division in matrices. So suppose I tell you, you know what? Solve 6x equals 18 without using division. I don't know how. And then you think about it for a little while and you say, okay, you want to make it hard on me? I'll treat that. So when you tell me 6x equals 18, I'm going to say, you know what? I'm going to multiply 6 by its inverse. What is the inverse of 6? The inverse is the reciprocal, meaning 1 over 6. So this would be 1 over 6 times 6x equals 1 over 6 times 18. I didn't divide, I multiplied. 1 6 times 6 is 1, 1x is x, and the right-hand side is 3. So we are going to do something almost identical to that. The problem is, how do I take the reciprocal and multiply it? Where is the inverse? We call it the inverse, which is the reciprocal in algebra. How do we find it? Okay, so today we are going to learn one method, and then next time I will show you another. Um, so first of all, let's introduce a couple of theorems in linear algebra. The first one says there are three statements and they are equivalent statements. What does that mean? It means you don't have to prove all three. If you prove one, you have proved all three. A has an inverse, is invertible, meaning has an inverse. If you already know that, then use it, but sometimes you don't know. So you would say the only solution to the system of linear equations, matrix A times matrix X equal matrix 0, is the trivial solution. What is the trivial solution? The trivial solution is x1 equals x2 equals x3 equals everything equals 0. If you tell me x plus y plus z equals 0 and 2x minus y plus 3z equals 0 and whatever, I say, okay, so put x equals 0, y equals 0, z equals 0. That is called the trivial solution. If that's the only solution you can find, then A is invertible. But sometimes you can get multiple, infinite number of solutions if one of the equations is not independent of the other two. So in that case, you will get infinitely many solutions, right? So that means A is not invertible. Or sometimes you cannot find, um, so that will not. And the third one is that A and I, what is I? I'm going to talk about it in a second, are row equivalent. What is the meaning of row equivalent? Meaning I can go from A to I, whatever I is, or from I to A through, um, excuse me, a limited number of elementary row operations, the EROs that we discussed in Gauss-Jordan elimination method. I, like we have one notice that when I say 1 6 times 6x, 1 6 times 6 is 1. So I can say 1x equals 3, and 1x is basically x, right? 1x. The identity matrix is a matrix that if you multiply it by any other matrix, making sure the size is correct, and we will talk about that later, okay? Then you get an you get the same matrix. So it's like it acts like one in algebra, okay? And if we say I1, it's just the number one. One meaning it's one row and one column because I has to be a square matrix. So I don't have to say I1 times one, like one row and one column. I know they have to be the same. I2 would be one along the main diagonal. We call that the main diagonal, and zero everywhere else. I3 would be 1 0 0 0 1 0 0 0 1. I10 would be 10 rows by 10 columns, and only 10 values would be ones, and 90 values would be zero. Okay. The second statement or theorem that makes perfect sense is that if I use A, the matrix A, and augment it by the identity matrix, remember when we augmented the right-hand side in Gauss-Jordan? Now we have two matrices next to each other. And then I go through a series of limited number of EROs that transform A into I, the same operations. So I'm not going to take matrix A and do operations on it until I get I and then go back and say, oh, what did I do to A the first step? So let's apply it to I. What did I do in the second step? No, you can apply the EROs to both matrices. If A can reach I, meaning A is invertible because A and I are row equivalent, the right-hand side would be the inverse. That's the trick. Okay. So I have in algebra it's trivial. If I tell you what is the reciprocal of 10, you say 1/10, 1 over 10. Remember, we didn't have division in um, we didn't have division in matrices. So if I have 10 and I want to find its inverse, I would say, okay, here is 10, here is 1. I want 10 to be 1. So what do I do to it? I multiply it by its reciprocal. So I'm going to multiply 1 by its reciprocal. So the left-hand side would be 1, the right-hand side would be the reciprocal of 10. It's something similar to that, but of course more involved. So let's take an example and see how we find the inverse of a matrix using elementary row operations. So nothing new. We are not going to learn anything new. We did that in um, in Gauss-Jordan elimination method, and then see how we are going to solve. Remember, after we find the inverse of 6, we multiplied it by the right-hand side. So that's what we are going to do. So we are going to write three equations in three unknowns. Let's say x plus 2y plus 3z equals 5, for example. Let's make an easy. Okay. And then let's make 2x plus 5y plus 3z equals 3. And then let's make x plus z equals 17. And we want to solve for x, y, and z. We need to find the value of those. So let's start. The first thing it tells you, write your augmented matrix. So 1, 2, 3, but we are not going to write 5 next to it because that would be Gauss-Jordan, right? Now, first we need to find the inverse of this matrix, the matrix on the left. I want to find the inverse of that. No, that cannot be z. I'm sorry. That's 8z. So they add up to, I pretty much gave up the answer. But anyway, 108. Instead of writing 5, 3, 17, we are going to write the identity matrix by the same side. If it's 3 by 3, I have to write I3. And now we are going to do exactly what we did with Gauss-Jordan to make this the identity. So let's see. I have a 1 in the main diagonal entry in column 1, so I'm not going to do anything to row 1. This has a 2, and because I am in the first column, I am only allowed to add or subtract multiples of row 1. If that's a 2, you subtract 2R1. But when you subtract it, I'm not just going to subtract from these 3. No, I'm going to subtract from the whole row because the operations I'm applying to A, I have to identically apply them to I, so that by the end of the time, the end of the day, when A becomes I would be the inverse. Also here I have 1, so subtract R1. Let's see what we get if we do that. Of course, the first row, I didn't do anything to it, so it stays the same. 1, 0, 0. And then I'm going to subtract twice the top from the bottom. So 2 minus 2 is 0, 5 minus 4 is 1, 3 minus 6 is negative 3, 0 minus 2 is negative 2, 1 minus 0 is 1, and 0 minus 0 is 0. Then you're going to subtract top from bottom. 1 minus 1 is 0, 0 minus 2 is negative 2, 8 minus 3 is 5, 0 minus 1 is negative 1, 0 minus 0 is 0, and 1 minus 0 is 1. So was nice, I ended up with the first column. So I'm going to move to the second column. Realize that the main diagonal entry is a 1 also, like it was here. So I don't need to do anything to row 2. I'm going to keep it the same. But then, because I'm in column 2, I can either add or subtract multiples of row 2. That's a 2, so you subtract 2R1, R2. This is negative 2, so add 2R2. And that will take you, of course, the middle row won't change. When you subtract twice, you say 1 minus 0 is 1, 2 minus 2 is 0, 3 plus 6, because you are going to subtract 2 from negative 2 times negative 3 is positive 6. 4 plus 1 is 5, negative 2 plus 0 is negative 2, and 0. And then add twice R2. 0 plus 0 is 0. Negative 2 plus 2 is 0. 5 minus 6 is negative 1. Negative 1 minus 4 is negative 5. 0 plus 2. Oh, I'm sorry. Did I add twice? Yeah. Yeah, it's correct. For some reason, I thought I subtracted, not added. 0 plus 2 is 2, and 1 plus 0 is 1. So now I'm done with the first two columns. The third column has a negative 1, so I'm going to multiply that by negative 1. Let's just make it easy. So let's multiply the whole row by negative 1 instead of rewriting it. Okay? Here, I am in column 3, and column 3 now has a 1 in the main diagonal entry. So all what you have to do is just to subtract 9R3 and add 3R3. So what I will end up having, of course, is an identity matrix here because you're going to subtract 9 from 9, and here you're going to add 3 to 3. So you will get 1, 0, 0, 0, 1, 0, 0, 0, 1. But let's see what happens to the right-hand side. This is still 5, -2, -1, because we are not going to touch that. But then now we say 5 minus 45 is -40. -2 minus 6 is -8. 0 plus 9 is 9. In the middle row, I'm going to add 3 times the bottom. So 15 minus 2 is 13. -6 plus 1 is -5. And -3 plus 0 is -3. So now I found the inverse of A to be -40, -8, 9, 13, -5, -3, and 5, -2, -1. So how do I solve for x? Here we are going to introduce the multiplication of matrices, which if you don't know how to multiply two matrices, I will have a session like exactly to cover that material. But for now, let's say, in order to find the first answer, which is x, the second would be y, the third would be z, is that I take the first, if I want the first row, I'm going to take the first row from the first matrix times the first column, and there is only one column of the second matrix, and multiply them element by element. So the number of elements should be the same. If this is 3, then those are 3. The number of columns here equals the number of rows here. If not, I cannot multiply the matrices. -40 times 5 is -200. -8 times 3 is -24. So now we have -224. 9 times 17 is 153. So when you do the math, you will get, how on earth is that? I did. Is that an 8 or a -8? I must have done something wrong. Of course I did. That's not an 8 or a -8 at all. Here it is. When we subtracted 9, -9 times -2 is +18. Oh, +18 minus 2 is +16. How did I do that? -9 is 9, okay. And then here we added 3, 15 minus -6. Okay, I think this is correct. So this is +16. So we had -200 plus 48 plus 153. For the second row, I have 65 minus 15 minus 51. Here I get 25 minus 6 minus 17. So the answer would be, if you add those, you get 201 minus 200 is 1. This is -66, so -1. -23 plus 25 is 2. Okay, I'm sorry. I don't know how I did that. I didn't do anything. I rewrote. I don't know how I got -8. I really don't. Okay, so the answer is x equals 1, y equals -1, and z equals 2. You have to check your answer to see if it makes sense. If x is 1 and y is -1, you get 1 minus 2 is -1 plus 6 is 5. So this is correct. 2 minus 5 is -3 plus 6 is +3. 1 plus 16 is 17. And that's it. Again, sorry for the math error. I apologize. I don't know how I got that. In fact, oh, I see it now. I added 3R3 to R1, not -9R3 to R1. I used this instead of that. For I don't know how it happened, but when you multiply 3 by -2, you get -6 minus 2 is -8. Yeah, I'm getting old. So thanks for your time. Next time, I'm going to show you another method of finding the inverse of a matrix and use it. Maybe we use the same one to show you uh, how we are going to do that to solve a system of linear equation. Thank you very much for your time and hope to see you soon. Bye.